All right, I present here. Hello, everyone. Welcome to week 3 about learning, neural networks, AI, and large language models. Today's topic is going over backpropagation and large language models. This is quite an interesting topic because I actually specialize in large language models, and I've been working with them for quite some time. I would say around 2 years. First started around GPT-2, which is about 3 years ago. GPT-2 came out. I was able to fine tune the model to use the context and history from my conversations and basically imitate my texting behaviors. And that was kind of the start because I thought it was a funny prank and thing, and it actually turned into a really cool thing. Now I'm making a startup called Airy, and we use local large language models on edge devices like your phone to do a bunch of AI tasks, and I've learned so much about optimizing these models. Super interesting topic, but let's go over some of the basics and learn some of the basic concepts surrounding backpropagation and large language models. So, first up, let's quickly recap on neural networks. What did we learn about neural networks last week? Oh, and you might hear me sound very weak. It's because I am sick. I like I'm about to have a fever, so apologies if I sound slurred or I'm not saying the right thing. So, first up, let's talk about backpropagation. At its core, neural networks, recap. At its core, a neural network is designed to learn from data. As we learned from last week, we learned about how neural networks are just layers of neurons, and each neuron has some kind of activation function. There are 3 types of layers: input, output, and hidden layers. And these layers kind of indicate what the model is trying to learn or output. We learned about weights biases and how that affects a model's performance. Rather, how they can get the right answer a lot of times. But now we're going to go over a different topic, a different concept within this. It's called backpropagation. So it works like this. It takes an input, like 2 pixels of an image, passes it through the interconnected layers of neurons, produces an output. And that identifies what's in that image, just like we talked about last week about the numbers, digits, and counting the pixels. Each pixel uh, basically traced back to a neuron, and the group of neurons activated will tell you what number it's going to be. But how does it do this accurately? More accurate. This is where backpropagation comes in. So before we get there, we need to talk something about the cost function. So the learning process actually starts with a cost function, which measures how well the network is performing by comparing its output to the correct answer. We want to minimize this cost, then essentially reducing the error between what the network predicts and what's actually true. To find the minimum of the cost function, we use an algorithm called gradient descent. Imagine you're standing on a hillside and want to find the lowest point. The gradient tells you the direction of the steepest descent, the quickest way down. In neural networks, the gradient tells us how to adjust network's weights and biases to most effectively reduce the error. And here's where backpropagation shines. It's the algorithm we use to calculate the gradient. It works by propagating our signal back up to the network layer by layer. By doing so, we figure out how much each weight and bias contributed to the overall error, and we can adjust accordingly. Let's say we're training a network to recognize handwritten digits. We show it an image of number 2. If we miss it classifies it, we know the output should change. We want to increase the activation of the neuron associated with it, and decrease the activation of the other digits. These desired changes are propagated adjusting weights and biases. This is how we can increase our accuracy. Now, calculating the gradient using all the training data can be computationally expensive. That's where stochastic gradient descent comes in. It uses many batches of data to approximate the gradient, making the training process much faster. So that's backpropagation in a nutshell. Now let's shift gears. Let's talk about large language models. These are the powerhouses behind chatbots and AI systems. Now, at the core, LLMs are incredibly good at predicting the next word visually. When they trained on massive amounts of data to generate coherent, contextually relevant responses. But the question is, how do they do it? Well, pretty simply. Start with a bunch of parameters, essentially parameters that are initially and they're trained on a massive data set. During training, they're shown examples of text and make predictions about the next part. Using backpropagation, they adjust their parameters to get better. Training these models requires immense computational resources. They use device model architectures called transformers, which allow them to process text in parallel. This is actually discovered at Google in a research paper, I think around 2017 or 2018. And they rely heavily on GPUs to handle the massive calculations. The amazing thing about LLMs is their behavior emerges with complex interactions of the parameters and the training data. This makes them incredibly powerful, but also challenging to fully understand. They are potentially really complicated. They have lots of different metrics to analyze, basically decipher which model is better than the other one. Some of these metrics include stuff like confidence window, max sequence length, parameters, or parameters, which is the random numbers, is pre-trained, what is a quant, all these kind of things affect performance and accuracy of the model. So you might have heard GPT, ChatGPT, might have heard of, you might have heard of DeepSeek. So DeepSeek R1, ChatGPT, let's say O1. These things are kind of the modern innovations at this time. Can't wait to see what's next. But these models are known for their reasoning or chain of thought. We've come to a place with large language models that we don't just predict the next word. We try to simulate a large language model, essentially generating thought. And once that thought is generated, then it generates an answer according to that thought data. So, for example, if I told O1 ChatGPT to give me a pasta recipe that doesn't use tomatoes, it's going to think long and hard about what tomatoes serve in pasta, why would you use tomatoes in pasta, is it a good idea, all these different things to come up with the most accurate answer it can. Now, as someone that's been in the space, I personally have interest with procurement as a research and development and worked with many researchers to create LLM solutions using open source LLMs. I'm a very big FOSS guy, fully open source. And as well as my startup uses open source language model. The cool thing is, these models, there's so many, where they're trained, how they're trained, what they're good at, all these things. There's so much data. If a model's good at something or not. These days, you can even run a model on your phone. Initially, it might be really slow. That's fine. Actually, in my startup area, I came up with a way to do really fast CPU inferencing using a special package called XNMPack, which essentially spreads LLM responses and CPU cores and enables for crazy metrics like 500% increase in efficiency. If you want to see the demo, let me know. It's actually a really, really cool thing I can develop. And my app will most likely be the first one to utilize that and be the fastest local inference you can get on the market. But regardless, it's enough selling. In short, Backpropagation is the key to training neural networks, and large language models are pushing the boundaries of what AI can do. Both rely on massive data, powerful computation, and clever algorithms. They're shaping the future of how we interact with technology. Let's see how it goes from here. Maybe we get AGI in the next 5 years. I'll buy a lottery ticket. Alright guys, thanks for watching. We'll see you next time.